This is the first drive of an electric Toyota Tundra. The project is about half completed, but it's drivable on the test battery that I've been using, which is a lawnmower battery. That obviously offers very limited range and power, but it's able to get the truck up the driveway, which has about a 6-degree incline. And the transmission is from a Lexus LS600h, but without the 5-liter V8. And others who have used this transmission in battery EV projects have dynoed this transmission at about 225 horsepower electric. And this will eventually have a much larger battery pack that will enable it to produce that kind of power to make the truck more drivable on the road. But of course, unless I get a 100 or a 200 kilowatt hour battery pack, this is going to be pretty limited in its usefulness and practicality as a pickup truck. But in terms of the capabilities and the basic specifications of the truck, I would like to be able to achieve at least the same horsepower, torque, and range as the original truck had. And that's why in the second half of this build, this Tundra is going to receive something a little bit special. Something to keep that modest battery pack charged while it's driving down the highway. And it's not a solar panel.
What the hell is even that?
Daddy, chill.
That's right. Edison Motors and myself have ourselves a race to build the world's first plug-in hybrid turbodiesel pickup truck. And now for those of you who like the boring details, I'll go into the specifications of the powertrain and show you how this 2-liter 4-cylinder engine will be adequate for this 3/4-ton truck. But before I do, I'll show you the engine bay one more time to show you where this motor is going to go and kind of the basic configuration as it is now. And the truck currently has an MR2 power steering pump and an electric brake booster pump from a smart car. So I use this diagram from the Oak Ridge National Labs technical report on the LS600h inverter and motors versus the Camry. And I pulled together a topological comparative diagram of these various EV topologies that people are using. The original versus the battery EV versus actually what nobody's using, but what I'm going to be using. So the original LS600h powertrain consisted of a 2UR 5-liter V8 that produced peak horsepower of about 390. And the total peak horsepower of that powertrain was only rated at just under 440 horsepower. So the electric power being contributed by the electric motors in the eCVT transmission was only about 40 or 45 horsepower. And that limitation was due to the entire electrical system, including the battery, but primarily due to the DC to DC converter that lives inside of the inverter housing, which can and should be bypassed for this application. So without the small and limiting battery pack that's only 1.8 kilowatt hours in the LS, and without that DC to DC converter in the inverter, I'm aiming to be able to produce at least 200 horsepower electric with my 20 plus kilowatt hour battery pack, hopefully 40 kilowatt hour, but whatever it is, it should be able to deliver 500 amps, roughly 500 amps at 350 volts, which would give over 200 horsepower. Of course, it'll have an onboard charger, unlike the original vehicle, to charge the battery at home. And one modification that people are doing to use these transmissions of battery EV is locking the planet gears and welding them to the planet gear carrier in the transmission. So right now I just have it locked with the original flywheel, and then I have that flywheel mounted to the plate that's also used to mount the front of the transmission to the frame. So I just have that kind of locked up. I didn't want to weld anything for various reasons. Regarding the VCU here, the vehicle control unit, we won't be using the original Toyota Lexus vehicle control unit. We're using the Zombieverter, which is based on the Open Inverter project software. So it controls the Toyota inverter using synchronous serial. And we can do everything with it that we need to. So the difference between the battery EV topology that people are using and mine, one small difference is the transfer case. I'm not using the original transfer case from the LS600h. That was an all-wheel drive Torsen center diff transfer case. And so you'd basically have full all-wheel drive. And this is a 4x4, so I'm actually using the original Tundra transfer case, and it happened to match the splines of the transmission, the L110F transmission from the LS600h. So it plugged right in. I had to make an adapter plate for it to bolt it on. but it plugged right in. So I'm going to use the original four-wheel drive control, original transfer case, and have mechanical four-wheel drive. So that's one primary difference between my vehicle and the Edison Motors design. They have basically a series hybrid. This is a series parallel plug-in hybrid. So this topology over here shows what that will be. So I'm basically using a combination of the original and the battery EV topology that people are using. So I will be using an engine on the front, not a 390 horsepower engine, but a 140 horsepower engine. And I'll show you here in a minute which engine I'm using. So I'll still have an onboard charger for the battery pack. I'll have a hopefully much larger battery than this, but I'm aiming for a power output, a continuous power output capability of about 340 horsepower, although I probably will be using much less than that. The original Tundra, I have it on the video. I forget what it is, but it was under 300 horsepower. So I'm going for slightly better than the OEM horsepower capability. And I want to go a little bit more into the horsepower capability and the torque capability of this powertrain. I'll start off particularly with the new diesel engine, the 2-liter CJAA TDI engine that is rated at a peak horsepower of 140 horsepower. That's at least 100 horsepower less than the engine that was in it originally. But over here on the right, I've got some figures for the energy requirement for an electric vehicle at 60 miles per hour, given an efficiency of 500 watt hours per mile and 300 watt hours per mile. These are two examples of a relatively low efficiency EV and a higher efficiency EV. So a low efficiency EV would require about 500 watt hours of energy per mile at 60 miles per hour. This truck, I don't know what power or what energy it's going to draw per mile. It's a relatively large profile vehicle. It has a lift. So at 60 miles per hour, it might end up requiring more power than that in order to keep the battery full. But we'll see. We'll find out. It does have relatively efficient electric motors. They are permanent magnet AC motors instead of induction motors. Tesla in the early days was using induction motors, and the efficiency of induction motors is in the low 90s. PMAX or permanent magnet AC motors are in the mid or upper 90s in terms of efficiency. So we'll see how that goes. But at a lower efficiency, it requires 40 horsepower continuous. At a relatively high efficiency, it would require 20 to 30 horsepower continuous. So this engine, of course, is rated 140 horsepower peak, but diesels do like a high duty cycle. I do think that this engine will be capable of providing 40 or 50 horsepower or more continuously, given that I have adequate oil cooling and glycol coolant cooling. So I probably will be using the same radiator as the Tundra had originally, because it was a new radiator, in fact. So it's in good condition. It should be able to dissipate adequate heat, but we'll find out. This is all experimental, but I am confident that this engine will be able to provide the continuous power needed to keep the battery full. And the battery will be able to provide adequate power for that electric side of the powertrain to be able to produce well over 200 horsepower. So in terms of thermodynamics and power per drag or per driving up an incline with a heavy load, for example, or pulling a trailer, I'm confident that this truck will be able to perform at least as well as the factory truck. And you may be wondering about torque, and I'll go into torque now, because I haven't gone into detail about it through this video yet. But this transmission on the output shaft without the transfer case bolted on is actually a 2-gear transmission, low gear and high gear. The low gear, I believe it has a 2-to-1 gear reduction relative to the high gear. So in low gear, with the internal planetary gears between the first and second motor, it's capable of producing about 1,000 foot-pounds of torque on the output shaft in low gear at 500 amps of current into the inverter. So 1,000 foot-pounds of torque, of course, is plenty of torque for a pickup truck. But this does also have the JF1A transfer case from the Tundra. I'm using the original transfer case. And the low range gear reduction in that transfer case is 2.61 or 2.62 to 1. So theoretically, on electric power only, this truck can produce roughly 2,600 foot-pounds of torque. It may not be able to drive very fast at that torque. So if I really needed that much torque, and I honestly, the drive shaft and axles and the differential might not even survive that. So just assume 1,000 foot-pounds of torque is the peak torque output of this powertrain on electric power only. Given that the battery can provide enough power, enough current to provide that torque, this powertrain can definitely provide plenty of torque to do the normal duties of a vehicle, a passenger vehicle, and also a work vehicle. So it should be able to haul. I don't think I'll pull anything heavier than what the original truck was rated for, but I am confident that it will be able to pull at least what the original truck could. So we'll see. It's all experimental, but I wanted to kind of go into those details about the capability of the powertrain in terms of the diesel engine, transmission, the transfer case. It should be a pretty good fit. Thanks for watching.